Hi, I'm Jan, and today I want to guide you towards a lot more advanced example of using Edge Impulse to build a predictive maintenance system. Um, in this video, we'll go over using custom DSP blocks to extract features from a signal where you already have an idea of what you're looking at. We'll be looking at using the feature importance feature to see what parts of the spectrum actually convey an interesting signal. We'll use that then as an input to train an anomaly detection model, and together then we'll actually take all of that and I'll show you how you can integrate that into your own device firmware, and that actually shows you how to do a custom DSP block implementation with our SDK as well. So yeah, let's get started. So what are we trying to build? Here we have a data set that Jenny, one of our user success engineers, has created of a fan. And because this is an anomaly detection, predictive maintenance system, I have two states. I have the off state, at which case there's barely anything happening. This is attached, an accelerometer attached to the fan. And I have a nominal option. In this case, the fan is spinning around normally. So naturally, we can see that there's something happening, of course, but what that exactly is, we're not sure yet. It's pretty high resolution, or pretty fast rotations probably happening on this fan. So let's go and dive into that a little bit. So Edge Impulse comes with a number of settings and a number of kind of pre-processing blocks. So the very first thing that I think in general we want to look at when we're looking at data is to see what type of information can we get from this signal to start with. So in Edge Impulse we have a whole bunch of pre-processing blocks. For example, spectral analysis, which is really great for repetitive motion. But the way that our spectral analysis block works is that it tries to find peaks in the signal. So let's take a look at that. So a really key part of that is actually that it tries to find, let's see, a nominal sample, is that we disable the filter, is that we try to find these peaks and that will we store. That is here actually not that interesting. We are, as you can see, there's a lot more vibrations or more rotations happening. What we're probably more interested in is to see the energy per frequency band. So, for example, what is the amount of energy between 1 and 2 hertz after an FFT, 2 and 3 hertz, 3 and 4 hertz, etc., etc., etc. So this block almost does what we want because it does an FFT and it does then spectral power density, but we want our buckets to be more well spaced. So how hard is that? Well, actually very easy. So Edge Impulse supports custom processing blocks. So any of these processing blocks that we have, you can just take and modify and use them again in your project, or even in your organization, and make them available for everyone in your company. So all of the processing blocks that we have, so the ones that you see in the Edge Impulse Studio, are listed under Edge Impulse /processing blocks. So these are all implemented in Python. For example, here you can find the spectrogram processing block, the spectral analysis processing block. These blocks have a parameters file, so that tells you what they are, what they're good for, and the CPP type, so that's what the C++ function is going to be that implements this, so that's important later in the SDK. And it has parameters, so are we using a filter, yes or no, what's the type, what's the cutoff frequency, etc., FFT lengths, and here the DSP.py, which is the actual implementation of this. The cool part is you can write this in basically any language. So we have examples here in Python. As you can see, you can use SciPy and NumPy and kind of all the libraries that you're used to. If you rather write this, for example, in MATLAB, which might be cool because it very often has a way of generating the corresponding C or C++ code straight from there, that is fine too. It's a very basic, easy specification where there's data coming in. So the data coming in is the actual raw data, the number of axes, and then all the parameters. And then what you pass out is features, so the process data, and then graphs. So I've cloned this one here locally, and this is my custom DSP block now. So I made a spectral analysis v2, and here we actually get the frequency and power characteristics of the signal over time. And the way that I do this is that we write our codes in, say, generate features, is we go over the range from 1 to the half sampling frequency. So here we're looking at a 100 Hz signal, so that will yield, we go from 1 to 50 Hz. And then for each of these, we'll create a kind of power band of half a hertz prior and half a hertz after the center. So we'll generate these bands. So these are all hertz, and then we get the total energy. So what do we get for out of this block? That is the total energy in the signal, so the root mean square of the signal after the filter. That's just an interesting feature, makes it easy to plot. And then one feature per energy band. So here we'll have 49 of these. So we have 50 features per axis, so 150 features in total. This is very straightforward, right? We do an FFT and then we look at the power buckets. But we could just as well do really complex things here. So let's look at features over time. Let's take the derivative of that feature, do all kinds of other like filtering over that. Really easy to implement, basically in this Python library or in any other language that you want to go with. So this is what you want. So to start this block, I can say start the DSP server. So that runs on my computer web server. If you are an enterprise customer of Edge Impulse, you can push this to your organization and we host it for you. Then in a second tab, I'm going to run ngrok. So ngrok is a reverse proxy that makes this block available over the internet. So here is my forwarding address, and I copy that. So here we go. All right, so let's go to Edge Impulse and actually add our custom processing block. So to do that, go here to add custom block, throw in the URL, and there we go. So we have our spectral features, which is now our custom block. And let's feed that into this. All right, so you'll see that we actually look at a much wider spectrum. So now we look at 0 to 50 Hertz, which is what we want. We'll need a longer FFT to take advantage of that. So there we go. We probably want a high pass filter because we don't really care about frequencies that are anything between like 0 and 2 Hertz. There's probably not information in that because we have a rotating fan. So let's take a look at some nominal data. And this is cool. So we see a nice peak here. It's around 31 Hertz, and then another like smaller peak around 49 Hertz. That is probably the frequency of rotation. Not entirely sure, but that's something we're going to figure out. So on some other sample, we see an interesting peak around 15 Hertz, which is half the 31 Hertz. So maybe this is a bit slower. We don't know, but this is just reference data, and from that we're going to dive into seeing what actually the interesting buckets are. So I'm going to save this. And I'm going to generate features that go over all of this data. As you might realize, we don't have any kind of anomalous data in here, right? It's literally just the fan is operating normally or the fan is off, which is the two states. But from that, we're going to see some interesting things already. For example, what are actually the frequencies that are present? So which of these buckets has a much different number between these two states? And that's probably the normal rotating frequency of this fan. So we're expecting something, I guess, somewhere around 31 Hertz, at least on one of the axes. and then something around 49 Hertz. So let's take a look. So that's what we're doing now. So right after creating features, we can determine our feature importance. And that is, it does it first for all classes, and then for all the individual classes, plotted against everything else. All right, so we have our data. We plot all of the samples here in the Feature Explorer. If you've done some stuff with Edge Impulse, you'll be very familiar with that. But here we have a feature importance, and that is really interesting to kind of get an insight of what's happening. So the most important feature that is found is the root mean square of the full signal on the y-axis. That is definitely probably an interesting feature, but it also doesn't tell us much. Because if this fan is rotating, there's a lot more energy happening, but it doesn't tell us like if that's the right frequency or if there's something weird going on. The more interesting frequencies that we see here is, well, we have energy on the y-axis around 39 Hertz, on the z-axis around 32 Hertz, which is what we saw earlier, and then a little bit higher as well, 47.5, 48. We can dive in, and these are kind of the key frequencies that we see on this device, so that helps us a little bit. So let's take 3 of these and train a anomaly detection model with that. Okay, why an anomaly detection model? Well, what we're interested in is when something starts deviating from the norm, right? So we have the key frequencies when the fan is on, and when there's something anomalous happening, for example, the fan is not rotating in the right at the right speed anymore, or something weird, or something else is going on, an obstruction, or someone is touching it, we'd expect a difference on those specific frequency bands, because those are what kind of happens normally, and that's probably an indication of what's going on. So let's go here and add an anomaly detection block. And our anomaly detection block, we can specify the axes that we're interested in, and then we're going to run a clustering algorithm over that. So this one is really interesting. Let's add that. Let's take this one as well. That's kind of surprising. We didn't really expect that. I didn't really see any peaks there around 39 Hertz, but it's an ML model. It's probably better at this than we are. And let's find the high frequencies here. And I should do it on the z-axis on 47.5 to 48.5 as well. So we've taken 4 of these features, and that's going to be kind of our anomaly block. So this is some data that is learned. So you can plot stuff here, say, okay, let's plot the y-axis around 49 Hertz against z-axis around the same frequency, and these are kind of all the clusters that we've learned that are normal data. In addition, we're going to train a neural network as well, and that's going to classify. So yeah, what are these 2 things? So on one end, we have the normal classifier. That's going to tell us, do we have a normal fan, so is the fan on, or is the fan off? And then in addition, we have an anomaly detection model, and that will actually tell us, is the fan operating normally? So together, these 2 things kind of give us both insight in whether the fan is on or off, useful, and then also whether that behavior is normal or abnormal. That's at least the idea. All right, so this is kind of what we expect, right? It's 100%. It is really easy to determine whether the fan is running normally or whether it's off. So this part of the network should be trainable really, really easily. And now we have a good baseline. So let's test this out. So we can go to live classification, and we've loaded a number of nominal samples and some off samples, and we collected some anomalies as well. So first, let's take a look at some normal data. So this is good, right? So we have 5 windows that we generated from this 3-second sample. All of them are classified as nominal, which is what we expect. So the 3 outputs that we get here are the score for nominal and off. These will always calc up to 1. And then we have an anomaly score, and that is how abnormal is this data? Like how well are these axes that we selected earlier, these frequency bands, how common is this distribution over those frequency bands for this specific sample? And you can see that's like clustered here into a cluster of a lot of normal data. So this is actually not anomalous, so very low score. We can do the same for off, that's normal state. And that actually follows the same pattern. So 1.0 for off and an anomaly score below 0, which is an indication that this is not an anomalous sample. So our baseline works, but we just trained this on nominal and off data. What happens if we throw in a obstructed sample? So this is a place where the fan is obstructed and it starts probably vibrating a little bit differently. So because the neural network only knows about on and off, so nominal and off, we get a 1.0 for nominal, that's fine. But then we have an anomaly block. An anomaly block actually gives a really high score. So for the stuff for normal and off mode, we saw this hovering around 0, or a little bit below 0 even, which means it's in a cluster. Here we actually have a pretty high anomaly score. So that's an indication that it's far outside of this cluster. So as you can see, these orange dots are very far outside of normal operation of this network, and thus are anomalous. Really cool. So we have a base model. So, but we're now just cherry picking a couple of examples. Let's see how well this model actually performs, and we can do that through model testing. So in my data acquisition, on the training set I've collected, an even number of off and even number of nominal samples. But in my test data, I have 2 different states of anomalies. So one is shaking the device or touching the fan, and an obstruction where something is happening there. So let's actually dive in and rename the expected outcome of obstruction and shaking as anomaly. So now we have 3 classes: anomaly, nominal, and off. And we can use this to score our complete network to see how well it's doing over each of these 3 classes. So we go to model testing. So this is all data that the model has never seen while training. And now we're going to ask it to score. So it's going to score both on the neural network. So is this on or off? And then also, is this an anomaly, yes or no? And we'll use the data as we specified here to get to that. All right, so now becomes the interesting part. So in general, this model is performing really well, right? So for off, it's basically always right. For nominal, we actually have a number of samples, 36% of our samples, that are actually flagged as an anomaly right now. So let's dive into that. So we see here actually a number of samples, but these are actually flagged as anomalies. So let's dive into that and see what is going on here, and if you can fix that. So we'll see actually an anomaly score of about 2 here. And if you remember, for the anomalous score that we saw earlier, we saw like 20 or 25. So this threshold might just be too low. The threshold right now, we can set it here, is 0.3. And after that, we flag it as an anomaly. We actually now realize, when looking at our test data, that is probably too low. And maybe set it to 4 and see what it does to our model. Potentially, of course, this has the effect of flagging stuff not as an anomaly when it actually should be. So let's actually go take a look at model testing. So previously we were 85%, and we had a lot of things that were anomaly and were predicted as anomalies, so we're pretty good, 90% correct. And let's see actually what this does after we reclassify this data. All right, so we're definitely a lot better. We had 91% of nominals are now classified correctly. Still a few are actually misclassified. We can dive into that. Let's take a look here. All right, so this is even a bit higher. Maybe we even want to set this threshold a little bit higher than we normally have. Or it could be that this sample is just vibrating a little bit differently than the other samples. So we might want to dive into that. Let's actually set this a little bit higher to 12, just to ensure that all of our nominals are correctly classified. And then we're going to dive into the anomalies and see how we can fix that. So let's go here. All right, so we now have all of our nominals are classified correctly. All of our off are classified correctly. And we have about 75% of our anomalies that are also classified well. And if you look at these kind of subclasses here, you see that obstruction is detected incredibly well. Shaking is not. So how can we go and dive into that? So now that we know actually where a model performs well and where it doesn't perform well, just saying anomalies, it does 75% is okay, but it's actually more interesting to see that that is actually happening on shaking data. Let's see if we can retrain our anomaly detection model on different axes to up that performance. So to do that, we are going to add a little bit of data to our training set. And the only purpose of this is just to see what are the interesting frequencies that are present on shaking but are not present on nominal operation. So I'll go into my training set that Jenny put together for me, and I'm going to add some shaking data. And I add it to my training set. So we're not going to train with this data, but rather we're just going to run our feature exploration over this, just to see what the interesting frequencies are. So if you look at shaking, for example, here in the graph, you see a really high peak a little bit earlier in the frequency domain. And that's probably going to be a hint. So let's run this, and then we're going to look at our feature importance after generating this data, where we also have the shake data. We're going to see kind of what interesting things we're going to learn from that. Right, so we now trained and we see our shaking data is a little bit more all over the place. More interesting here is the feature importance. So all of a sudden we see that the most important feature of this distinguishing between all three classes is this amount of power between 4.5 and 5 hertz. And we see here a little bit on 5.5 to 6.5 hertz as well. If we're actually going to look at how we can distinguish shaking, that becomes even more apparent, right? So here we see shaking against every other class. So what is the most important feature if we just want to detect that against? And it doesn't really matter if the other part is off or nominal. So we see this data around 3.5 to 4.5 hertz. So if you want to train an anomaly detection model that detects these things better, we want to add some more classes. So let's add the amount of power around 4 hertz on the x-axis. And let's look at all the data we had. So this one is probably a good indication as well. So we're adding, let's keep it at these 2 classes to our anomaly detection model. And those are probably a good indication if something weird is going on, because these frequencies are typically not present in very high with a lot of energy on either off or nominal state. So let's get rid of all the shaking data and retrain our model. So we're retraining again just a nominal and off, but now we're actually saying in our anomaly detection is learn on these lower frequencies around 4 hertz what normal is. And that goes into our anomaly detection model. So let's see what it actually has done to our model testing set. So previously we had about 25% of all our anomalies were misclassified. But with our updated model, we now see that actually all of our anomalies are correct, all of our offs are correct, and all of our nominals are correct. So now we have a well-trained model. It does really well on kind of this whole that set of anomalies. We didn't really train on all of this. We just looked at the data. And we now have a model that actually should work really, really well in the field. The cool part here is this data-driven engineering flow. This project is still there. So if you're in the field, you see that the device says, oh, this was actually normal operation, but one of your technicians says, oh, this was actually an anomaly. Cool, tag that data, get some of this raw data, feed it back into the project, and maybe look at what is interesting about these signals. Train this project again, maybe on different axes, and through this you can build a better model over time. All right, so now to deployment. So what we can do with Edge Impulse is take all of the code that we have and export it as a C++ library. Now this works kind of out of the box for all of our pre-built processing blocks, but we have a custom processing block here that we modified ourselves. How does that work? So let's go. Let's do a C++ library, export. And we get a zip file. And that zip file contains the Edge Impulse SDK, as well as a model parameters and a TF-Lite model folder. And those contain the neural networks, the anomaly clusters, DSP configuration, etc. To develop the C++ implementation of this, you don't need to run that on a board directly, you can do it on your computer. So we have the example standalone inferencing example project. And this runs on Windows, Mac, and Linux. You can just compile it down locally to go work on an implementation of the DSP block that you can run from our SDK. If you have something like MATLAB that can do this automatically, say I have my DSP code, I generate C code from this, awesome, you can plug it in there. So let's take a look at how hard it actually is and where you need to integrate that. So let's go to example standalone inferencing. I'm going to remove my current model here. And I'm going to add the model that we just created by just dragging it in. Cool. Then we also need an example, so we actually know if what we're looking at is actually correct. So we're going to go to live classification. And let's find actually an anomalous sample here in obstruction. And we'll take the raw feature, so that's the raw sensor data. And we throw it into feature.txt. The very beginning of this application is just looking at this file and parsing all of these features in and then calling the classifier. That classifier calling is kind of what the whole gist of it is literally this function. We run this learn classifier with the signal we just got from this features file, and then we print the results. So let's compile this application, and then we're going to call the classifier with its features file. All right, this fails with an error because it is looking for the extract PSD bands features function. And that's something we can't provide, right? Because that is a custom DSP block that we just created earlier. So let's take a look at how that looks like. So the function signature is here in DSP blocks. So what we pass in is a signal. So a signal is the complete, a signal gives you, it's a structure that tells us where to get the data. So here we don't have a lot of data, right? It's 2 seconds of accelerometer data at 100 Hertz. So that's 600 features. But we might have a lot of data that we need to page in from Flash, for example, so let's support that. Then we have an output matrix. That's where we need to write the code. Then we have a config pointer and we have the frequency. So let's take a look at what is in there. So let's go implement that. So our config pointer, that's something we get from model metadata. So that's of type EIDSP config PSD bands T. So these are all the parameters that we chose earlier in the UI, and you get them in here. So let's have a small implementation of this that just prints kind of what is the size that we need to output. And then we error out. All right, so the output matrix size is 1 by 150. And if you remember from our DSP screen, we output 50 features per axis, and we have 3 axes, so we expect 150 features in total. So easy. All right, so the Edge Impulse SDK is really useful for building and implementing these types of DSP operations because it has highly optimized vector functions for a lot of things, like scaling matrices, calculating FFTs over matrices, and it has implementations of these algorithms both in normal software for stuff without accelerators, but also, for example, code that uses CMSIS DSP to speed that up. So I put together, based on the function that we have here, DSP, and then the spectral feature. So this is the implementation of the spectral analysis block in Edge Impulse, but in high performance C++, all vectorized. So I built, because I based the custom DSP block based on that, I modified that function a little bit, and then this is that implementation. I'm going to just throw it in here. So it's very simple in all fairness, right? It gets the config, it gets a sampling frequency, it scales the signal if needed. Then we're going to look at every axis in one go. We look at the spectral power edges, and then we extract features. I'll throw the code somewhere on GitHub if you want to dive into that. But this does exactly the same thing as we done in the UI. So let's actually go run that. So we just implemented this one feature. The rest of the code is already there, right? All the neural network code, all the anomaly detection code, etc. So what do we get out of here? We first get our predictions, so nominal 1, but an anomaly score of 504.13. And if we look here in the UI, we actually see an anomaly score of 504.13. So this is all there. So now let's write a little bit of business logic here. So here we have our prediction. So it's kind of three states, right? We have an anomaly, we have nominal data, or we have off. So here we can say if, I think we said 20. Otherwise, we can look at our classes. So our first class is nominal and our second is off. And if it's neither that, so it's not an anomaly because the score is under 20, but we're not sure whether it's normal operation or off, we'll just right. Let's go compile this. So this is a very basic control loop that looks at the output of all of these things. So here we actually have an anomaly. And so let's take a look at another sample. So we can use, let's say, nominal here, normal operation. All right, throw that into features. Cool, normal operation. Awesome. Let's do a last one where we actually look at off data. All right, so that's off. That works really well as well. So we've gone through the whole exercise of building a custom DSP block both in Python and in C++. We've looked at using feature importance to select the right feature for an anomaly detection block. We've refined that based on anomalous data that we found we actually didn't trigger properly yet. And we've put all of that together into a project. So if you now want to integrate that into the firmware of your device, you can reuse the same code as is. So because we're using the primitives in our SDK, for example, stuff like, let's take a look. For example, here for NumPy scale. So that's a scale operation, which is one of the basic building blocks. That is actually implemented both in highly optimized vector math for ARM Cortex-M processors, as well as in normal operation mode. So this runs fine on both things. This kind of runs on every embedded system under the sun. So on our docs page, under running your impulse locally, we have a wide variety of places on how to run this and compile this down. So whether you want to run it on Linux, Mbed, Arduino, Zephyr, STM32, and literally anything else. This is how you have instructions on actually getting this from your computer and running it on the target itself. Yeah, so with that, I want to thank you for watching this. I hope it's really informative. I hope it shows that building these types of applications is not just let's throw a bunch of data into this and a model come out and we know exactly whether that's right or not. Working with machine learning is still engineering. It's just engineering on a little bit of different scale. Yeah, right? So rather than looking at the signal and then changing the control loop, you're adding data, analyzing that, you're still in the loop, right? ML is just a tool for you, or a way to kind of help you make decisions. And from that, refine that project as we go. So Edge Impulse is here to help. It is, yeah, on one end, Edge Impulse is a place where you can do a lot with very little code, but Edge Impulse is also an incredibly flexible platform where you can continuously look at these data-driven engineering decisions, make better decisions on that and refine that, and actually write code to do that as well. So if you already know interesting information about your signal, you know what a good DSP pipeline looks like, you know what a good neural network might look like for the type of data that you're looking at, that's something you can always do within Edge Impulse. So I hope this gave you a little bit of more insight into what Edge Impulse can do for you, and we can't wait to see what you'll build.